Welcome everyone. In this video I'm going to introduce the MAX31855 thermocouple module. I have a previous video on thermocouple module, which is the MAX31855, and I showed you its advantages and disadvantages. And for example, the most striking disadvantage of the 6675 was that we could not measure negative temperatures with it. So that's not so good sometimes, because sometimes we want to measure those. So then we have this other guy, the 31855, and this module is able to measure negative temperatures. In fact, the total range of this device is starting from minus 270 degrees Celsius, and it goes up to plus 1800 degrees Celsius. But here I should notice that this device comes in different packages, and it is compatible with different kind of thermocouples. So of course the most popular one is the K-type thermocouple, but we have others like J, N, T, S, R or E, and all of these thermocouples can be used with this module, but you always have to check which module you buy. So we are talking about this guy. This is the 31855, and it does not really differ from our previous guy, which is the 6675. So this was the one which I showed in the previous video, and for that introduction, please check the corner there should be a link. And I will not talk about this in this video. I just emphasize if something is very different from this module that I'm holding in my hand right now. So as you can see, the circuit board is really simple. So we have the connections, and let's start from the top. So VCC, GND, that's for the power supply. And now please pay attention. This device works with 3.3 volts. This is very important. So don't try to plug it in your 5 volt. It might work because mistakenly I also did that, but don't run it at 5 volts. It's only 3.3 volts. Please keep this in mind. And then again, we have a one-way SPI communication, so we don't have a data in on this module. But we have SO, which is the slave output, so this will send the data towards the microcontroller. And then we have CS, which is the chip select, so if you have multiple devices, then you can select the one that you are reading at the moment. And SCK, which is the clock. And then you see a solder pad here, which is for the fault detection. So what this thing can do is, if you solder this tab together, you are pulling the T minus part of the wire connection to ground, and whenever there is a fault in the wire, in the thermocouple wire, then it can be detected by the chip, and actually this fault will be indicated in the bits which are transferred to the microcontroller, but more details about that later. So yes, we have this small tiny board. Of course, it comes with a small terminal, and then the jumper pins for the 5 holes here to connect it to a breadboard or something like that. And I already have this thing wired up and with a display and everything. So the resolution of this thing is 0.25 degrees Celsius, but for more details, read the manual, because there are some limitations because of the linearity of the device and so on. So you will have a bit different precisions at certain temperature ranges. So this 0.25 resolution is the absolute resolution, yes, but then you also have a precision, so that also has to be considered. So let's talk about the details what I have here. So this is another K-type thermocouple thermometer. This will be used just as a reference. And then here we have an Arduino Nano. That will be our microcontroller, but any SPI compatible microcontroller is fine. You can use any kind of Arduino or Raspberry Pi or STM32 and so on. But for this very simple presentation, I just use this guy here. Of course, we have the 31855 module here already wired up, and here is the thermocouple. I just borrowed the same thermocouple I used for the previous demonstration with this guy. And then of course an I2C display, 16:2 display. So technically this is all about the device. There is nothing else than just to show you how it works. And actually the more exciting part will come after I show you this, because there is some tricks that we can play with when we are coding this code for the Arduino. And I will spend more time there because there are other tricks that you can learn and then use in further projects. So let's power up this device. So I'm again using a mobile charger, so just a simple USB connection, and then you should see the message soon. So it's just some welcome message. And then in the top line we have the internal temperature reading. So there is a diode inside the chip which is measuring the temperature, because that is used for the cold junction compensation. And then there is the external, which is the thermocouple itself. And now, as I try to avoid touching these things for a while, they are showing roughly the same temperature because they are at the same temperature. So now the reference or the cold junction temperature is at room temperature, more or less, and the probe is also at room temperature. And just for fun, I turn on this thing, and I don't know how visible it is, but now this is showing 26.1. So you can see that there is a slight difference between the two devices, but this is what we expected because none of them are really calibrated, so we just use them as some kind of comparison. So I clean this up a bit and I bring a cup of water. So this is some slightly warm water, so we can try to measure that temperature and see what we get with the two different devices. So this should be visible enough. So after waiting a bit, the temperatures stabilized until a certain extent. So you can see that this guy is reading 40.25 and then this is 37.3. So there is like 3 degrees difference between the two devices. But now let's say we are okay with this, and we cannot really do anything about that. But the main purpose of this video is not chasing the precision and calibrating all these devices, but just to show you a solid experiment where I make this thing work. So you can see that it works, and let's say certain devices differ from each other by, let's say, 3 degrees. Now as you can see, it's nearly 3 degrees difference. So this is what we got. And now I would like to go to my computer and show you the internals of this chip, and also show you how the SPI works. And then also I will show you the source code and explain it line by line. It's not too difficult, so it will be quite easy to understand, and then you will be able to tailor that code to your application. So let's go to the computer. Alright, so I copied the most relevant pictures from the datasheet here, and you can see the different things and tables. So let's start from the top left corner, and this is just the SPI diagram. So what we have to know is that the chip select pin has to go low, and then we start the SCK, so we clock out the data, and then starting with the MSB or most significant bit, we start to move out the data. And then after 32 bits we have the full data captured, so with the 0 we finish the transmission, and then the chip select goes back to high, and then we are waiting for the next signal. And we have to keep in mind that there is a conversion time which is around, if I remember correctly, 70 to 100 milliseconds. So you cannot read this thermometer very fast, because you have to allow the AD converter to finish the conversion. But I think 10 Hz is more or less enough for any kind of applications for us average users. And under this block diagram, we have another diagram which is just showing the same, but with the timings, and the most important timing that we have to care about or just pay attention to it is this TCSS. So this is basically the timing between the chip select going low and the clock starting. But I noticed that even if I don't add any delay, this number is too low. It's 100 nanoseconds if I remember correctly. So it will be just fine if you are coding like me. So I will show it in the code. There is no delay, but it still works. And then before going to these tables, I just show you the block diagram. So T plus T minus, here goes the thermocouple, and of course you have to take care of the polarity of the wires. So just take care of the polarity, and this is the switch that I showed you as the solder tab, so you can solder or connect the ground to the T minus, and this will be used for an open circuit detection. And then there are some fault detections here, S1 and S2, how they are shorted to the ground or the VCC. And then we have the most important thing, the cold junction compensation. So this is the 12-bit internal temperature sensor, which is usually just a diode. So that is feeding some sort of voltage to the AD converter, and of course we have the default voltage output of the thermocouple. So the combination of these two voltages will result in another voltage, and that is what we use to convert into digital data and then forward it to the computer via SPI. And once again, this device works with 3.3 volts. It's very important. So coming back to the table here, so we have 32 bits, and this will give us some headache, but we solve it, so don't worry about that. But just as some kind of introduction, the problem is that the SPI usually sends or receives the data in 8-bit packages, but this is like 4 times 8 bits. But we can deal with this. And also another headache or another challenge is that, as you can see, one relevant data, which is the internal temperature, is located here in this part of the code, but there are numbers after it and before it. And also the real data, what we really need, is between 18 and 31. That is the thermocouple data, and that is located at the end of the 32-bit code, but still we have this large amount of data, so we somehow have to deal with this, but don't worry, I will take care of that. And then I just put this description list here. This is just helping us. So you can see that we have the range of the bits, so that is starting from here until D18, and then you can see the nice description. So you can see that, okay, if we start from the MSB, most significant bit, so D31, and go down towards the D0, first we get the thermocouple data, there is some reserved data, which is always 0, and then there is a fault detection, and that goes 1 if any of these 3 things are triggered. And then we have the internal thermometer data, so that we can see, and then another reserved data. So as you can see, there is a 0 here and a 0 here. It's just something interesting that you can use it to frame your data if you want. And then after this, we have these 3 fault detection values, but they are more or less always 0 if you manage to wire everything correctly. So this is the first figure or set of figures that I wanted to show. And now I show you the source code, and we will jump to another kind of similar demonstration later on. So this is the source code, and I just basically recycled the source code from my previous introduction or demonstration where I used the 6675 module. And I also borrowed some code from my earlier demonstrations because there are some tricks that we have to do. But yeah, once again, 3.3 volt is the supply voltage and not 5 volt. Keep that in mind. So we are using the liquid crystal I2C library because we are using an I2C LCD, and I just put here the typical connections for the SDA and SCL connections, but of course on my website you will see the wiring and everything. But if you are using an Arduino, it's typically A4 goes to SDA and A5 goes to SCL, or if you are using an STM32 blue pill, then B7 is the SDA and B6 is the SCL. And then we just instantiate this, and you can see that we are using this address 0x27 and then 16 blocks, 2 lines. We need the SPI communication because that's how we communicate with the thermometer module. So we have to initialize or include this library. And then we have a few variables. So as I said, the data comes in 32-bit packages. So we need a variable, or we need variables which are capable of storing 32 bits of data. So we using the unsigned int 32. So the raw data, which is just the pure raw data coming out from the thermometer module, and then I will separate this into 2 other raw datas. One raw data will contain only the thermocouple temperature, and the other will contain only the internal thermometer's temperature. And finally, we convert these 2 temperatures into like Celsius degrees and store them in these 2 variables here. And then we need the chip select pin. I assigned it to the pin number 10, which is usually the default pin. But since I want to work with it manually, then I defined it. And then in the setup, since we need the chip select pin as an output, we have to define it as an output, and also we pull it high. That means that we are sort of waiting for the command, which will be the chip select going low, and then we can clock out the signal. So we start the SPI and we start the serial, because I also send the data to the computer. And then this can technically be a copy-paste part from your side, because this is just how you set up the LCD. So these are mandatory lines, so you have to initialize the LCD and the backlight of it, and then you put the cursor in the 0, 0 position, so that's the upper left corner of the LCD, and you print something up to 16 characters, and then we jump to the new line. So the second argument here defines the lines or rows, and then that means that I'm in the bottom left corner with the cursor, and I just print thermocouple, as you could see it when I showed you the device itself. I wait a little bit so the user can see this welcome message on the display, and then I clear everything, and then I will fill in the display with this function with those parts which are permanent, so they will not change during the operation. And from here I want to jump there directly, so I show you what is happening. So as you could see it on the or during the demonstration, there was a line with internal and there was a line with external, and those are permanently printed, and this is the code for it. So we jump to the first line, first block, and print this text, and then second line, first block, and print this text. So this is all regarding this function. This just runs once when we run through the setup. And now let's focus on the loop. So the main loop is very simple. We read the thermocouples, and I haven't put any delays there, so I put the delay here in the loop, because we are not doing anything where we need to run the loop continuously. So I can afford doing this. But this blocks the whole loop. So if you need something that that is more time critical, then this is a bad practice. And also I put a note here that according to the datasheet, we have to wait like 70 to 100 milliseconds to wait for the conversion. So this is 1000 milliseconds, so this should be more than enough, more than enough delay between two conversions. So then once we read the thermocouples, then that means that these two variables are filled in, and then we can refresh the LCD. So what happens there is written here. So we move the cursor after the text what we wrote in the print LCD, so that will be, let's say, the 10th block in the first line. And then we delete the part that we want to write, because if you don't delete, and if you printed a 3-digit number previously and now you want to print a 2-digit number, then the 3rd digit from the previous reading will get stuck in the display, and therefore you will get confusing data. So always you have to overwrite your previous number with some spaces. So I just put several white space here. And once you're done with that, you can print your number. But if you can make sure that you always print the same amount of digits, which is not always the case if you go from, let's say, 100 degrees to 80 degrees and so on and so on, then you can do this. But I just recommend you to always delete the contents before printing new data. So after we deleted that line, we just put the cursor back to the beginning of the spot where we want to start printing, and then we print the internal Celsius variable, which is the variable for the internal thermometer. So this line is wrong. And then we jump to the next line. We delete again. We jump back to the beginning of the blocks where we want to start printing, and then we have the converted value for the thermocouple. So then this will be the thermocouple's temperature. And then comes the most important part. So this is a bit longer than previously, but stay with me, please. So if we follow the table that is provided in the manual, then we have the following details. So starting from the 31st bit and going down towards the 18th bit, we have the 14-bit thermocouple temperature data. Then the next bit is a reserved bit, and then the next bit is a fault bit. And after these 2 bits, we have another set of temperature data, which is the internal temperature data, and then the rest 4 bits is just reserved data and some fault indicators. So, but I just put this here as a reminder. So it's very important to zero everything out, because otherwise, due to the operations that we do, we might confuse some numbers. So let's keep everything clear and clean. So let's put the chip select pin low, so then we can start clocking out the signal, and we are using the standard SPI modes provided by Arduino. So we begin the transaction, and then I use the same strategy that I used for my other video where I used the 24-bit AD converter, because there it was the same challenge. So the data which was provided by the AD converter was 24 bits long, but I only was able to step out 8 bit at a time. So I had to combine these data and shift the data and so on. So now I do the same, but I add one more step because I'm now stepping out 32 bits. So what happens first is we put the first block of incoming data in the raw data. So that means that shows up in the beginning, and then we have to shift it by 8 bits towards the left, and then we read the next chunk of the data and combine it with the previous data. And then now we have two data, so 16 bits together, and we grab that 16 bits and move it to the left by 8 bits again. So then we grab the next portion of the data. So now we have 24 bits together, and then we grab these 24 bits and shift it to the left by 8 bits. So now we can put the last 8 bits in our data, combine it with the previously captured one, and therefore we have all the 32 bits. And for this I actually have some nice presentation which I will show, but before that I will go through the rest of the code, because there will be other operations that I also want to show. So after we collected these 32 bits, we shut down the transaction, so no more clocking out data, and we pull the chip select pin to high. And then I start printing some data on the serial port, because I was curious about the integrity of the data. So this is the raw data, and then I print the same but in binary. So I see the bytes and bits. So this was just an example output. I put this here for myself as a reminder, but some numbers are sort of missing, maybe not the best phrasing, but yeah, they are not here, because I was reading too small number, because I was just reading room temperature data. And then first I wanted to take care of the internal temperature data, because that's quite simple. So what we have to do is we want to save the data in the new variable, the raw internal, and what we do is that we take our 32 bits data and shift out 4 bits towards the right, so we actually get rid of these 4 bits. But then we still have a bunch of data on the other side, on the left side of this data. So there are two ways to do it. One is an ugly way, but it works, and there is a more elegant way, which is elegant and it works, and it's just one step. So the ugly way is here commented out. So first of all, we can move the wall data that we have from the previous steps 20 bits towards the left. So then we shifted out all the data after the internal temperature sensors data. But then the internal temperatures data is too high up. So this is not the value that we want. So we have to shift it back to the original position. So we do the same shifting back to the original place. And what this does is that if there was anything after the internal temperature data, so for example that was also some fault bits and also the data from the thermocouple, then that gets transformed into zeros. But this is done in 2 steps and maybe not the best practice. But alternatively, you know which data you want to make 0. So what I made here is that I just used the bitwise AND operation, and then from this step I just used the AND operation and ANDed together my data with 4095. You will see it later why it is this number, and that also gave me the correct number. So then I printed out the data in binary, so I wanted to see how it looks like in binary, because for me it was more easier to check. And then I just convert the raw data into Celsius degrees and print it. And here I always assume that the thermometer is at least above 0 degrees. So then we don't have to care about the sign of the internal temperature data. But I will show you with the other, with the thermocouple data, how to do this. And if you expect to use your module in negative temperatures, then you can do that conversion for the internal temperature data as well. But usually the modules are stored at room temperature or close to room temperature, so we don't have to take care of the sign. So then we jump to our real data, so the thermocouple data. So what we want is we still use our raw 32 bits data and move the whole thing to the right by 18 bits. So that will eventually erase everything else than the data coming for the thermocouple part. So then here we check if our data is negative or positive, and this is done with this kind of operation. So what we do is we take our 14-bit number and we shift out 13 bits towards the right, so there will be one single digit remaining in this number, and that one single digit determines whether we work with a positive or negative number. If it is 0, then it's a positive number, so then this whole condition is neglected. But if it is 1, then it's a negative number. But then if that number is 1, that means that our number, if it would be considered as a positive number, it's a huge number. So what we have to do is we have to shift it back by 2 to the 14th power. So this number is that number, and that will give us the proper data for the negative temperatures. So then what we do here is basically we have the raw reading and we subtract this big number from it, and that will be the raw data for the negative temperatures. Then we print it, and then we convert it into Celsius degrees. And I mentioned it in the beginning of the video that the resolution is 0.25 degrees Celsius. So we just multiplied the bit number with this 0.25, and that gives us the Celsius data. And I promised you that I show you how this shifting, and how this shifting works. So let's do that now. So I made a table for this kind of map. So the map of the bits which are being shifted out from the temperature sensor. So that's what you see here, and I will explain everything, and I will also upload these tables as pictures to my website, so you can spend more time with it to understand it, because this is not only typical for this application, but whenever you have to shift bits or use the AND or the OR operation, this can come handy. So up here we have the original 32-bit output data, and then I highlighted that data which is relevant to the thermocouple, and I highlighted that data which is relevant to the internal temperature sensor. So you can see how they are located, and you can see the bit numbers here and here, and you can see the other things which are located in the beginning of the code or the middle of the code. So first of all, let's get the thermocouple data from the original 32-bit number, and this is a very easy operation. So this is our starting data or starting structure, and then we know that we want to get rid of basically this part which is highlighted in red, because that we don't need. And what you can do, and this is basically the most straightforward explanation of this, is that you count the amount of bits in this red region, and that is 18, and then you know that you want this green data to show up on the right side of the number, because you start to read your number from right to left when you create a decimal number from the binary numbers. So then you know that you want to move this part by 18 bits towards the right, so then this will be shifted out entirely because this disappears to the right, and then this will be here, as you can see it here. So this is what happens. And of course when you shift, then always a 0 comes out from the left side. So then all the, let's say, empty spots are just replaced by a 0 number. And then if we have a negative value, as I showed it in the code, we subtract this 16,384, but otherwise we just use the value that we get, because in that case we will just have non-zero numbers in the selected value, so between MSB and LSB. So now we want to get the internal temperature data, and I show you both ways. So this is the original structure, which I highlighted here. And then we want to get the blue region. So first of all, as I show it in this line, we want to get rid of these 4 numbers. So what we do is, you know that you want to get rid of 4 numbers, and they are on the right side of this original data. So we have to shift our wall data to the right by 4. So what this will do is that we get rid of these because they get shifted out towards the right, and then we get 4 zeros on the left because we shifted in zeros from that direction. And then we see that we still have this big green bunch plus these 2 numbers here. And then, therefore, we shift this amount, which I just highlight here, which is 20 bits, towards the left. So now we got rid of this part, but the problem is that our internal temperature data is ended up on the very left side of this number. And if this is considered as a 32-bit number and you start converting it into decimal, you will get a so huge number because this is the highest place in the 32-bit number. So then we have to put this back into the beginning of this wall 32-bit number. So then we shift back by 20 bits. So that is indicated in this line. So what happens with this blue block is that it goes back to the normal beginning of the 32-bit number, and all the other numbers are being replaced with zeros, which is perfect for us because then we can focus on just this number. So this is done. But I said that there is a more intelligent solution for this. So what we do is we have the original number. So we still do the same exercise. So we want to get rid of the 4 bits here, which are highlighted here. So we get rid of that. That's fine. And now we see that we have this set of number. So we still have these numbers selected, which we don't want. And now we use the bitwise AND operation. And we know that when you use the AND operation, you keep those lines where you are ending with ones. So what I do here is that I select those numbers which are in the same number as the internal temperature data. So basically this block is all 1, and if you convert this into decimal, that is 4095, and I let the rest of the 32-bit number to be 0. So then I end together basically this whole number with this block here, and then the result is this. So you get zeros as you wanted, and you get just the number from the internal temperature sensor. And the result is same in this line as in this line, but we saved 1 step, so probably it's a bit faster and better in terms of memory. I haven't checked it because none of them are requiring high resources anyway, but I think this looks a bit more elegant or smarter. And then finally I made an illustration for the 32-bit data shifting. So as I said, we can only get, let's say, 8 bits at a time, but our final number is 4 times 8 bits. So in total we have 32 bits. So what we have to do is we have to grab our portion of data, shift it, combine, shift it, combine. And that's what I show you here. So first we get the MSB of the 32-bit number, but this is just the first 8-bit block. So this happens in the code in the first line. And after that, we have to shift it towards the left by 8 bits. So then this 8-bit block ends up here, as you can see. So this is 8 bits away from the initial position. And then those numbers, since now we shift towards the left, we got 8 zeros coming in from the right. So then we can read the next 8 bits and immediately OR it. So we just glue them together. So that means that these zeros are being replaced with our next data, which is coming in, and that I call 16, because that will be the next portion. So this was the 8, this is the 16. So now we have these 2 blocks, and again we have to shift towards the left by 8 bits. So that's why they came here. So as you can see, they jumped 8 bits towards the left. And again, the very first block became replaced with zeros. And again, we can now receive the third portion of the 32-bit data. So that's the 24, I call it like that. And we use the bitwise OR operation. So we combine these 2 numbers together with the freshly came 24 block. So this is fine. So now we have to do another shifting towards the left. So now you see that these 3 packets are like here. And now you see that we got the zeros coming in from the right again. So this indicates the 8 bits shifting. And now we just one step away from our final thing. We read the last portion of the data, which I just indicated as 32 or LSB. This is the last portion of the main 32-bit data. So this is how you create the whole 32-bit data from 4 8-bit packages. So original data comes in shifting, combining, shifting, combining, shifting, and finally combining. And then this number is the number that we use here and here, and so on and so on. So I hope that this was clear enough. So coming back to the code, we basically don't have anything left. We just have to enjoy the product of this work. So now you can see that in the loop, we just read the thermocouple, we wait 1 second, we refresh the screen, and then we jump back to the reading, and so on and so on. And this goes endlessly. And you could see that it works with more or less okay precision. In this case, this is what we can get out of the system. So basically this was the demonstration. So I hope that this was useful to you. Please check the description of the video, and please also check my website, because I always upload the resources there, such as the schematics, the source code, and some other pictures which can be relevant to us. In this case, I will make some pictures for the bit shifting and the combination of the data, so people can understand it better. Yeah, I hope this video was useful to you. I hope you learned something, and see you in the next video.